Today we have a very special seminar. Our speaker is Dr. Deanna Hens from Goddard Space Flight Center in Maryland, Greenbelt, Maryland. So I want to tell you a little bit about her background. She did her undergraduate degree at the University of Michigan in Ann Arbor in the Department of Atmospheric and Oceanic Science, and her concentration was meteorology. Then for her PhD, she went to the University of Washington in Seattle, actually where she did both her master's and PhD degrees, and her advisor was Professor Robert House. And her thesis was about the structure of precipitation in tropical cyclones, the topic that she will speak about today. And so since 2011, she is a research associate at Goddard Space Flight Center. And she is continuing her interest in tropical cyclones, and interestingly, she is involved in a field campaign to investigate the impact of the Saharan dust layer on tropical cyclone formation. So let us welcome Deanna Hens.
Yeah, actually. Thank you very much for the introduction. And good morning, everyone. And I am very honored to be here, to have been invited to come and talk to you today. And like Sultan said, I will be talking about the basically influences of large-scale conditions upon tropical cyclone precipitation structure. And this was the topic of my PhD thesis, as was mentioned. And I like to start off with this image because it shows the various different cloud formations that can occur in tropical cyclones in its varying stages of development. And so what you have here are three different storms that happen to be in the basin at the same time. If I could figure out how to turn this, oh, there we go. And so we have a developing tropical cyclone down here in the Bay of Campeche. This is from a few years ago, so, but I just like it because you can capture all of these on one image at the same time. You have the remnants of a tropical system spread out over here on the eastern seaboard. And then finally, you also have a mature tropical cyclone here over the open ocean. And so you can see some of the varying different forms of these of clouds and dust precipitation that tropical cyclones can have. And the motivation of this research is basically we're still struggling to understand the basic functions of what's going on deep within tropical storms. So that has a direct impact on intensity change forecasts. Now, the track forecasts have actually improved pretty substantially, as our various models have improved their motions of the large-scale atmosphere, which largely governs where tropical cyclones go. But with intensity is another matter altogether, because that's so reliant upon the internal workings of the storms, which are inherently difficult to study because they're largely oceanic creatures. Now, it was funny because this is actually the first time I've been able to put this image up and show that there's an actual slight improvement in intensity change forecasts. You can see that towards the end of this period, those forecasts start to, the errors, these are the National Hurricane Center's official forecast errors for intensity, are actually starting to come down finally. And that is, I think, largely because of improvements in models, improvements in model resolution, things of that nature. However, you can still see, especially in a shorter term forecast, that it's still largely flat, and this is since 1990. So you can see that there's still a lot of work to do in understanding the basic mechanics of tropical cyclones so that we can better improve this. Now, this would usually be the point I show a image of the kind of damage that tropical cyclones do to motivate why work in this area. But obviously, you guys' recent experience with Sandy last year, Irene the year before that, kind of doesn't make that necessarily necessary. So obviously, there's a lot of reason why we're interested in this, both because tropical cyclones are just inherently interesting phenomena, but also because of the large amount of damage that they can do. Now, like I said, hurricanes are largely oceanic phenomena. They spend most of their time over the open ocean. We usually only get to see them when they're making landfall and being modified by their interaction with the land. So over the years, our ability to get observations has been fairly limited by that. We can fly aircraft into them, but those aircraft have to be able to travel long distances. We have satellites, but satellites have limited observational capabilities. So largely we've been having to rely upon models and what observations we have. Now my particular favorite way to study, well, pretty much anything, is through radar. And the reason why is because it gives you an idea of the kind of precipitation that is going on within the tropical cyclones, and also if the radar has Doppler capabilities, can give you an idea of the kinematics and the dynamics of what's going on as well. So this is actually a ground-based radar showing the landfall of Hurricane Charlie in 2004. And I like showing this because it first introduces you to what a radar can show you if you're unfamiliar with it, but also gives you an idea of the various different structures that we're talking about within a tropical cyclone. So what you see here is the large swirling bands of precipitation. Now, the intensity of the colors, for those of you who aren't familiar with how radars work, this is radar reflectivity. And that is related to either the number of particles that are scattering the radar beam, and or the size of those particles. Basically, the take-home message being, it's a lot of rain. And especially here in the center, it's really a lot of rain. But you can see all the various different structures that are swirling around the center of the storm into this high reflectivity region here in the center. So to take a step back and try to identify what are the basic common features within a tropical cyclone, this is an idealized schematic of the typical radar reflectivity signature that you see within them. Now this is from HAF 2010, it's a review article basically on tropical cyclone precipitation. And so this basically highlights the various different typical structures that you see. So starting with the outer edge, you have these large banded features known as the rain bands. Out here in the outer edges, you have, we refer to them as distant rain bands, outer rain bands. You see them referred to different ways, but they're usually relatively disorganized, either scatterings of individual convective cells. Sometimes they organize into kind of more squall lining features. As you go closer to the center, you see that the rain bands start to get a more organized structure. They form more coherent lines. You may see more coherent structures within them, until finally you reach this high reflectivity feature in the center. That corresponds to the eyewall cloud, which is the main region of uplift within a tropical cyclone. So you get very high rain rates, very deep precipitation, and every once in a while, as this image shows, you can get more than one. And the other thing to mention is that these bands of high precipitation surround a usually reflectivity-free region known as the eye, where there's no precipitation happening, or very little. Every once in a while, you can get more than one of these features. So that's when we're having concentric eye walls. The storm may be undergoing what's called as eye wall replacement cycle. So these are the basic features that I'm going to be focusing on in this talk. The thing is about this image is that this is only giving us a horizontal plan view of what's typical of a tropical cyclone. The goal of my research is to basically add the vertical information to that basic outline and say, okay, that's great, what's happening at the surface, but how is this precipitation forming in the vertical? What kind of associated air motions go along with that? Now, we have the basic idea from some of the research I've done for my master's work, looking at especially precipitation with the rain bands, so we can associate what we see within the radar reflectivity to what we already kind of know is fairly common within convection within hurricanes. So I'll be taking a statistical approach to look at how these reflectivity structures happen across a sample of many different storms. The second objective of this is to look at how these features change based on changes within the storm's environment and what's going on with the storm itself. Because of course, hurricanes change in organization and intensity. They get impacted by sea surface temperature, changes in the environmental winds, things of that nature. So I want to look at how do those typical reflectivity structures change with the influences of these other factors. Now, I'm going to be talking, all this work is actually composed of 3 papers. I'll be focusing on the 2. One's focusing on the eye wall, and one's focusing on the rain bands today. There's a 3rd paper that looked at concentric eye walls as well, but I won't be going into that one in this talk. To do this, now I mentioned that our satellite capabilities are fairly limited, but they are pretty much all we have. And so what I did is I took a sample of swaths from the TRMM precipitation radar, which is the very first spaceborne radar that we've had. And it's been up since 1997, so my sample size goes from 1998 until, it was put up in late 1997, so my sample goes from 1998 through 2008, 10 years of data. And this gives you an idea of the sampling that TRMM has. It scans from 40 to 40 over the, and it gets a really good idea of the various precipitation features going on over the tropical oceans. This is this image is actually from the microwave imagery that's also on board TRMM, so you can see the various different clouds features. And actually you can see, I believe this is Hurricane Katrina here over the Gulf. So you can see that this satellite's very capable in real time to capture tropical cyclones, among other tropical precipitation features. So basically what I did is I took the swath of the precipitation radar and I organized them into various different things. And to give you an idea of what TRMM buys you over some of the more traditional ways of looking at tropical cloud features, this is a swath. This is actually Hurricane Katrina again, back in 2005. And you can see the plan view of the radar reflectivity. So you see the banded features associated with the rain bands. You can see a portion of the eye wall here. But the advantage of TRMM is that now it's adding information in vertical, at very high resolution at that. TRMM's vertical resolution is 250 meters, which is extremely high. And so you get really detailed vertical profiles of the precipitation as a result of that. And so you can see the deep and intense echo associated with the eye wall, and then the various banded features associated with the rain bands, and various other convective elements embedded within the storm. So this gives you a lot more information than looking at microwave imagery or some of the various other tools that we typically use. So what I did, and this is what was unique about the study that I did, was that instead of saying, okay, this is eye wall, this is rain band, this is thing I can't identify, I actually just did a systematic way of breaking up the various swaths into a series of annuli and also a series of quadrants, which I will get to later, to organize the reflectivity echoes in a way as the distance of both as a function of both azimuths and distance from the center. And to do this, this whole analysis is based basically on the eye diameter of the storm. And I should mention that this study is only done on storms that reached hurricane strength, so category 1 and higher. I did not look at tropical storms or below in this study. But I did this basically based on the center location and then the eye diameter, and then the rings are a function of distance from that.
Just a quick question. Yeah. So what's the width of the swath?
It was 215 and then went to 250 after the boost. So and that was the other reason why I had to take a statistical approach, I should mention, is because with the narrow swath width, you obviously can't capture the entire width of a tropical cyclone with one swath. And so I'm combining the data of many different storms to get at this statistically rather than looking at individual cases. So from there, what I did is basically created what are called contoured frequency by altitude diagrams, otherwise known as CFADs, of this reflectivity data. So starting with this, I could say take an individual ring, such as this one here, and from there construct a histogram of the various different reflectivity frequencies that are seen within that particular ring. Now from there, you basically do that as a function of height. You do that for every level within that particular ring So basically creating almost like a topographic map of the frequencies of the reflectivities within that particular ring. And you get something that looks like this. Now if you take a cross section through it, you'll basically get, like I said, what looks like a topographic map of those frequencies here. And I'm going through this because I'm going to be showing these kind of diagrams a lot. What this buys you is that it gives you an idea of how those frequencies change, what these frequencies change with height, which gives you an idea of your intensity, and also your microphysical pathways as well. It's how are particles changing as a function of height. And I did this for every ring and every annulus and sections thereof of these different swaths. So to begin, I'm going to start by talking about what is a symmetric structure. And basically what I mean by that is looking at those full rings. How does the reflectivity structure change as a function of distance from the storm center? And I like to start off with this because I want to start at the center and work my way outward. And this is a picture of Hurricane Katrina's eye wall. And this was actually taken with my camera. I didn't take it though. I was actually out in the rain bands of Katrina on this particular flight. We did a research mission called RainX back in 2005, and so the point of the experiment was to study the rain bands, but we did, had to scoot in the eye every once in a while too, just for fun. Not really just for fun, but I like to show this because this is a perfect example of a phenomenon that happens with the eye wall cloud, where you get this beautifully sloping orientation of the eye wall. And we call it the stadium effect in the hurricane world. But this is a perfect function of the kind of dynamics that you see within the eye wall. So this is from Emanuel 1986, and this shows what's known as the secondary circulation of hurricanes at its most basic and fundamental. So basically, when I talk about the secondary circulation, the flow within hurricanes being inherently spiraling can be broken into two components: the circular motion and then also the in, up, and out flow. And that in, up, and out flow is the secondary circulation that I'm referring to. And so this is what this image is depicting here. Now, because of the the force balance that happens within hurricanes, because of the particularly high winds involved, you basically get this inflow along the ocean surface, and as the air is going along, it's picking up sensible heat, it's picking up moisture from the ocean surface. Some of that air gets exchanged within the rain bands as it goes. When it reaches the eye wall cloud, it actually abruptly turns upward, and it goes upward along these lines of constant angular momentum and theta e. Now, when a storm is well balanced, that particular slope that occurs is usually right about a 45-degree angle, which is what gives that beautiful stadium effect. However, embedded within that flow, that in, up, and out flow that you also have buoyant elements embedded within that larger flow. And so we can see the perturbations upon this overall flow that can result in little buoyant towers kind of popping up off the eye wall. And this is important because this part is not often discussed, because this inherent flow is not buoyancy driven, but this part is. And so you see a mixture of those two things when you're looking at the reflectivity signatures within the eye wall of structures. So take a look at what I mean. This is the CFAT of what I call ring 1, annulus 1. That's the very first one. That's the one containing the eye wall. And the things I want to point out about this are two things. One, so this is 30 dBz, which is already a very healthy rain rate if you do a ZR relationship with that. But you can see that the lower portion of the CFAT, the part below the melting level, is centered right about 30, which already means, yes, you have very intense rain. On average, you have very intense rain within the eye wall. That's kind of an obvious statement. But you can see that the spread within that can vary fairly widely, anywhere from down here, which would be, I believe that's in the 15 to 20-ish range down here, all the way up to over 40 dBz. Now, this yellow region that I'm going to be referring to a lot is what I'll be calling the modal distribution, and this is where your normalized frequencies start getting above 50%. of what the maximum frequency is within these profiles. The greens and blues are the lower frequency occurrences, and I want to refer to those as the outliers. And I want to point that out because how both the spread and the placement of this modal region basically gives you an idea of what is the typical structures that you're seeing within this particular region. This blue and greens are kind of your more perturbations upon that, and your more variability on top of that. So, like I said, you have a very intense, low-level reflectivities. You have very deep. This is 8 kilometers here, so typically the eye wall is getting up to, the most intense part of the eye wall is getting up to 9-10 kilometers, which is very deep. Now your outliers, however, are getting even deeper and even more intense than that, going over up to sometimes 50 plus dBc. So you can see there's a mixture of various different things going on here. Now to compare that to just run-of-the-mill oceanic convection over the tropical ocean, which would basically be the convection I saw outside of the areas defined to be a part of the tropical cyclone. You can see the difference that I'm talking about here. So this profile is almost completely centered below 30 dBc. Your outliers aren't even, they're breaking 40, but not terribly in a very common way. The bulk of your structure is below 8 kilometers, and even the outliers are not reaching all that terribly high. So again, on average, your eye wall is a much deeper, much more intense convective feature than your more run-of-the-mill oceanic convection. Okay, so that gives you a general idea of what's going on with the eye wall. Now we're going to move further out into the rain band regions. And I wanted to come back to this because you can see that, again, there seems to be a break in what kind of happens between the rain bands in your more distant regions, farther away from the influence of the inner core of the storm, and your rain bands that are within what's known as inner core region, where they're more organized into more coherent structures. And that's going to become important because, before I keep going there, the reason why there's been a lot of debate within the community about the importance of rain bands. There's been suggestions that really active rain bands suppress hurricane intensity. There's suggestions that the exchange of air that's going on within the rain bands can feed low theta E air into the hurricane inflow, thus damaging the storm's ability to intensify. This is based off of my master's work. This is again from House 2010, but this is a combination of both mine and another person in my group's master's research. And basically what we're finding is that since these rain band features, even though the individual convective elements aren't all that terribly impressive, as a group, organized into these very large mesoscale bands, the rain bands actually can have a pretty substantial influence upon the storm circulation as a whole. And that's largely because they are en masse moving vorticity, advecting vorticity around in such a way that can actually enhance a secondary jet that often is found within hurricane rain bands. So if you're increasing vorticity and moving into such a way to form these jets in the mid-levels out here, then the further question from that is, okay, what does that do to the storm? If you're basically advecting all this vorticity out in further reaches. That's still an open question and still a subject of research going on. So back to the various different kinds of features that we see out here. So this is, again, showing the eye wall CFAD that you see here. Again, deep, intense, etc. Now this is the CFAD for the regions 3 through 5, which were the rain bands that are closer in to the storm center, compared to the outer region rain band, one that you see here. So you can see that one difference already in comparison to the eye wall. The general structure of these is shallower. And one thing that's interesting about the inner region rain bands in particular is that this low-level distribution is starting to tighten pretty considerably, suggesting that the kind of precipitation you're seeing there is much more uniform than you see in either outer region rain bands or in the eye wall. Also, the upper level structure is much more tightly packed, much more uniform. So this is going to be important, but this is just to show that these rain band features are inherently different in structure than what you see in the eye wall. So just focusing in on those two regions, this is again the CFAD for the inner region rain bands versus the outer. And to point out some features about these regions, first of all, this is the percentage of echo coverage for the different regions. Just saying, okay, where are there pixels of reflectivity and where aren't there? And this is based on TRIM's sensitivity. So these are all precipitation size of particles. But the red is showing the inner region rain bands, the blue is the outer region rain bands. So what you're basically seeing is that in general, the inner region rain bands have pretty significantly higher just general coverage of reflectivity than the outer region rain bands. Now this is probably largely due to the fact that the eye wall itself, as in that in-up and out flow, is spewing off ice in the upper levels in copious amounts, which then gets blown around in the upper atmosphere until it eventually settles out somewhere. Most of where that settles out is in these innermost regions. And so this structure that you have in the upper levels is relatively high, high uniformity, low reflectivity is largely, I think, a large part to due to that. You generally get more sparse in the outer regions, probably because we have mostly individual conductive scales that are kind of out there doing their own thing. Now, the other thing to point out is that as you move from the inner region to the outer region, the percent of pixels that are defined to be convective, in which that basically means, do you have a core pixel or group of pixels that are high reflectivity, isolated, they don't have high reflectivity around them, so basically your little convective cores. That fraction goes up significantly with distance from the storm center, where you have very few in the innermost regions, and it goes out to pretty much being mostly that in the outer regions. The other thing interesting to point out about this is that, in general, as I mentioned before, your mean reflectivity is higher within the inner regions in the lower levels, but it actually gets less in the upper levels, which is again what I was talking about before. You have that concentration of low reflectivity in the upper levels. But one thing, and this, when you're dealing with these CFADs, you stare at them for ages and ages and ages. One of the challenges was, how do I communicate what is in these CFADs to anyone else but me? And so I started looking for different ways to present the data that would pull out the information that I was seeing through CFADs. But one thing I ended up stumbling across was this value here. This is the kurtosis, which is the fourth moment on the mean, statistically speaking. And kurtosis is related to two things. It's a measure both of how peaked versus how flat your distribution is. It also is a measure of how thick your tails are. So if you have a normal distribution, your kurtosis would actually be a 3, but you can subtract off the 3 and make it 0, which is what I did here. But as your kurtosis goes positive or goes above 3, your tails start to get thinner, your peaks start to get steeper. And the converse is true when it goes negative, it starts to get flatter, your tails start to get wider. And this is basically what this is showing here. So in the low levels, we have a negative kurtosis value, basically meaning that the distributions typically are relatively flat, which is what you can see that here. And also your tails are starting to get a bit thick, which is fine. It's just basically showing that you have a fair amount of variability in the low levels. In the upper levels, however, the kurtosis starts going positive, and that's showing, again, a very peak distribution, relatively low variability, which you can see here based on the peaks in distribution. Now, there's this interesting kink that happens in the mid-levels, and that's right about the level of the melting layer. But what's fascinating about this, and this is what really started getting me interested, is that you can see in the inner rain bands, for one thing, overall, your low levels are less flat, so there's, relatively speaking, more peaked and thus more uniform than your outer rain bands in the low levels. But also that this kink is much bigger in the inner rain bands versus the outer rain bands. And what I think is going on here is that this is basically showing this pinch that you can see here at the melting level. You see the bright band here that happens within the inner region rain bands that is not nearly as significant as what you see here. And I think what's going on here is that because of the high level of shear that's going on within the inner region rain bands, you have that inflow in the low levels, the high outflow in the upper levels. You're getting a lot more of that in the inner regions than in the outer rain bands regions, where you're further away from the storm, the broader storm circulation. I think what's going on is that what's going on below the melting level is a distinctly different regime of convection than what's going on up here. And I think what's going on up here is that you have, that's basically showing your ice outflow that I talked about before coming from the eye wall. So you have large amounts of ice, small ice particles traveling out here, convection that's going underneath that sheet, that in the inflow in the lower levels. So I just thought it was very interesting how the kurtosis of these profiles was able to pull that information out in such a distinctive
Well, I
way.
have a small question.
Yeah.
So I understand these are composites from several storms,
Yes.
right?
Mhm.
So, but is the number of data points throughout the diagram the same? The number of that you have averaged?
So these frequencies are all normalized, and so the number of points that they represent in terms of what kind of samples you got for the different regions does change, just because, again, like for example, when you're talking about the eye wall annulus, it's a small region, and you don't always get perfect eye, swaths that go over the eye. So that would have less frequency than, say, some of these outer regions where there's more frequent coverage. And so going back to then how does some of these larger scale, the external phenomena start to impact the storm? I'm showing this because this basically gives you the full picture of what SST does. In that, when you have higher SST, and when I define high SST, I define it as 28 degrees Celsius or greater. That's generally considered the optimal temperature range for a tropical cyclone. Marginal is defined to be 26 to 28. And that's defined as for a mature storm, that's fine. For a not so mature storm, that's that's really borderline. Below 26, storms typically aren't considered to be able to form, and they don't typically do well once they get that. And unfortunately, because of TRM's scanning geometry, I didn't have a large enough sample in those low SSTs to be able to do any kind of analysis on. Only had, I think, 4 overpasses or something like that. It was very low. So I focus mostly on these. And basically what this is showing is that the black line is the full sample. So when you look at the high SST storms, you generally have a larger convective fraction than you have in the marginal SSTs. However, one thing that was interesting about this was I talked about those outliers versus the modal distributions I talked about before. The thing that's interesting about this is that those outliers changed substantially. You definitely had deeper, more intense outliers within the high SST cases, but the modal distribution actually didn't change that much. So that kind of suggests that tropical cyclones, at least once they're doing well and are already well formed, they may not be as sensitive to SST changes as we originally thought. There's probably other factors that are going on to influence their intensity on top of really warm or really cold SSTs. So it's more of a modulating factor, but doesn't seem to be the factor in determining their basic structure. Now, looking at how some of these profiles change with changes in intensity, this is the eye wall. Now, I think I'll actually get to this in a bit, but when looking at the eye wall, you do see a very substantial change in the profiles when you're looking at weaker storms, the category 1s and 2s versus categories 4s and 5s. And so we can see here is that basically the whole distribution shifts to much lower intensities, lower depths, and in general is a weaker circulation than what you see here into much stronger storms, and which makes sense because that whole the whole circulation of the storm, both the tangential and the secondary circulation, are going to be more intense in a more intense storm. Now this was a really interesting thing that I pulled out of the study that I was not expecting at all. And this is looking at the mean reflectivity and the kurtosis of the rain bands in weaker, stronger storms. So the weaker storms are the cyan, which unfortunately is not showing up too well on this screen. And then the magenta is the stronger storms. And what you see is that in the stronger storms, you have a pretty distinctive separation, both in intensity and in that general distribution, peakedness, and uniformity, et cetera, in the kurtosis. You can see that they're pretty distinctly different between the inner region rain bands, which are the solids, and the dashed is the outer region rain bands. But what was interesting is that in the weaker storms, those profiles become very similar. So you can't really see the difference of the lines because they're pretty much, for the most part, sitting on top of each other, except for this little bit in the upper levels. Which suggests that there seems to be something that is controlling the structure, especially of the inner region rain bands and the stronger storms, that is not there within your outer region storms. So could that be that secondary circulation with the eye wall pumping all that ice out? Could that be a modulating factor? Is it the changes in the inflow-outflow structure that's changing the shear profiles within those regions? That's not clear, but one thing that is clear is that they are, in the stronger storms, they are distinctly different than they are. And when the storm is weaker, they're very much more similar. So that's an interesting thing to continue to look at. So, okay, so I've been looking at the symmetric structure. Now I'm going to start looking at how does these structures change with azimuth. And one of the primary drivers of that is the presence or lack thereof of environmental wind shear. So this is a PMI image, microwave imagery of Hurricane Rita on the day that she was strongly sheared. And so you can already see that a lot of the storm, you have a lot more ice on one side of the storm than the other, and that's very typical in a shear in that a lot of the storm tends to get blown to one side in the presence of that. So to further that point, this is from Channel 2006, and basically what they showed is again that asymmetry in rainfall, where you tend to get a much stronger rainfall signature on the down shear left side of the storm. So the shear vectors pointing towards the top. You get more rainfall in the down shear left side of the storm, and you get a much less rainfall in the up shear right part of the storm, which is a very, very well-known and defined signature. And so I want to look at, again, how does that manifest in the vertical structure with mine. So what I did is I took the in-set reanalysis, and I just did the deep level shear of the 200-850, which is a pretty standard levels to look at. And I broke down this analysis into quadrants based on the shear vector. So, you'll see the down shear left, up shear right, and down shear right. And I'll be referring to this as I continue on. So what does the eye wall look like when you break it down this way? This is just, again, the whole sample. And what I did is that I took these quadrant CFATs and I subtracted them. I subtracted off the overall CFAT for that ring. So I subtracted off the total CFAT of the eye wall off of each quadrant. So the reds show you where you have more points in that region, and the blues show you where you have less. And what you see is that you basically are starting to see the evolution of the convection as it's forming, building, and decaying as it travels around its top tropical cyclone, a process which has been documented in case studies before. So now the fact that we can see this statistically is really interesting. So what you see is that you have a prominence of points, of extra points, up in the upper levels here in the down shear right, which is suggesting that your convective perturbations upon the mean eye wall circulation are getting their beginnings in the down shear right quadrant. As you move downwind, now you're starting to see more points in the lower levels, which is suggesting that you have your convection building, but the rain, everything in tropical cyclone gets blown around like crazy. And so where something forms and where it actually rains out are often two completely different places. So what you're seeing here is that you have the building of convection here, it's rain actually falling out down here in the downstream left. And then as you start traveling around, you start seeing the reflectivities shift to lower intensities over here until now in upshear right, you have very weak reflectivities being predominant over here. So you can see this progression of the building, the rain out, and then the decay until you have nothing over here. And what usually happens when you're looking at a sheared eye wall is that you see very, very strong reflectivities on this side and next to nothing on this side, oftentimes. And so this basically confirms this is consistent with that basic idea. So moving on to the rain bands. Now rain bands, especially in closer to the center of the storm, are not symmetric animals. They are inherently asymmetric. And they often organize into, the innermost ones in particular, are often organized into a complex known as, it's been called the stationary band complex, which is related to the shear that the storm is under. So this is one that this is the rain band study I mentioned I did off of Hurricane Katrina in 2000, this is published in 2008. Basically just documenting different changes in convection along the length of the rain band. And this was important because, for a couple reasons. One is showing that this is the mass transport that we're seeing within these different sections. And so this K1 is related to this most upwind feature here. This is K2, K3, and K4. So basically you're moving from upwind to downwind as you go down the page. So you can see that your mass transport is changing pretty significantly from what's very typical for convective features. So you have a net upward mass transport, mostly in the mid-levels here, and that's related to your potential vorticity generation of various other things. But as you move downwind, an interesting thing happens. Now, convection, as it typically builds up decays, it turns into what's known as stratiform precipitation, which you have a signature of upward, you can have upward, remnant upward motion still in the upper levels, but now you're starting to see the downward motion in lower levels, and that's very common. But the reason why I'm saying that what we're seeing in the CFADs is it's a mix of different things going on, because the other thing I noticed is that in this downwind region, we had actually two different profiles. We had what you would typically associate with decaying convection turning into stratiform. You also had this signature that had relatively little mass transport at all. And this was interesting. It's like, okay, this is a stratiform classified region. What is this? And it seems that what actually is going on here is that you're getting a lot of fallout, again, of ice, probably again coming either from the rain band convection itself or from the eye wall. So you have to be very careful when you're partitioning precipitation between convective and stratiform within hurricanes, because the stratiform precipitation in general can have two different sources, and you might not have this classic mass transport profile that you see here associated with it, because this part doesn't, this part out here doesn't have that associated with it at all. So you have to be very careful in that partitioning, because it has dynamic implications, especially when you're talking about putting this information into a model. So anyhow, basically this is showing the different, how the rain bands differ by quadrant. And so you can see that in general, your echo coverage, the solid line, is your downshear left quadrants, both in the inner and then the outer rain bands. Your echo coverage, for the most part, in downshear left tends to be greater. It gets to be at a minimum in the upshear right. So again, agreeing with that general rainfall displacement associated with shear. The other interesting thing about this, though, is that you can see the progression of the formation and the transition of convection through the rain bands. This black line here, this is the convection fraction, showing that in general your convection is where it's forming and how it's traveling along. So in the outer regions, you have your upshear right with your has a high convective fraction. As you move inward, then transitions more into the downshear right, so suggesting that the rain band convection is kind of becoming more convective along the band. And so then you get into inner regions where your convective fractions get very low. And so again, showing that general change in structure, both as we're moving from the outside inward into the storm and also around the storm as well. And then this is basically showing again how your reflectivities tend to be more intense on your downshear left section in the inner rain bands. In the outer rain bands, it's not so one quadrant versus another quadrant. It's actually just more downshear versus upshear. It's a much looser signal in the outer rain bands than it is in the inner rain bands, where it does become more focused towards the downshear left. So from all this information, I decided it was time for a new conceptual model for all this stuff to put this all together. So I updated it, basically showing these features, but now in relationship to the actual shear information that I pulled out of the study, because the schematic that existed up to that point actually ended up happening to be amazingly accurate, but there was no information along with it. Why was it drawn this way? So now we actually know, it's like, okay, this is how these features vary as a function of your shear vector, which is pointing towards the top. And so you can see, again, you have your sparse, more loosely organized convection out here in the outer regions. It becomes more organized, more intense as it's traveling around, and until it decays and becomes more stratiform or stratiform-like down here in the downshear left and in the left of shear side in the rain bands. And even though it's harder to see, the build-up, the rain out, and then the decay of the convective cells within the eye walls is also depicted within the schematic. So, but again, that's all the horizontal information. That's all great, but I wanted to now add the vertical information to this idea. And so this is the corresponding vertical image, and this is taking a slice from the left of shear to right of shear side. And basically, again, this is showing your more uniform, homogeneous, stratiform-like precipitation on the left of shear side, your deeper, more intense eye wall on this side. On the other side, your weaker, less intense eye wall, and then your more convective rain bands on the right of shear side. Finally, I should mention shear really quickly. Basically, this one is pretty easy. Higher shear makes the storm more asymmetric. Your asymmetries between the different quadrants and the different sides of the storm becomes more severe the higher your shear goes. And so you can see here that your mean reflectivities in the low shear storms are more similar. You can see a kind of left of shear versus right of shear difference on in the low shear cases. Once you get into the higher shear cases, you start seeing that more things being pushed over into the left, distinctly into the left of shear quadrant, which is this kind of purple line here.
What do you mean by low and high? What was the...
The breaking point in this was 7.5 meters per second. So below that was considered low shear, above that was high shear. So to conclude, and I'm running a little bit out of time, so I'll speed it up a bit, but the general structure, the typical structure of eye walls being deep, intense, with even deeper and more intense outliers embedded upon that general structure. The rain bands, on the other hand, the inner region rain bands being more uniform, more homogeneous. What convection there is typically squashed into the lower levels, and that distinctive separation between what's going on in the upper and lower levels, which I think is probably the most interesting part of that. The outer region rain bands tend to be more sparse, more convective, and you can generally see more connection between the upper and lower levels within the outer region rain bands. And how does that modify based on these various factors? Well, impact of the higher SSTs, you tend to get a little bit more of that cellular convection, those more buoyant perturbations. With higher intensity, the eye wall tends to be stronger, tends to be more intense, but the vertical constraint on the inner region rain bands also gets more intense. And so you have higher rain rates overall, but also that everything in the eye wall tends to get squashed even more to the lower levels than with your weaker storms. And finally, with the higher shear, basically the asymmetries grow with the higher in shear you get. So to wrap up, and I'll go through this really quickly, this is what I'm doing now. So now I'm over at NASA Goddard. All the work I talked about I did over at the University of Washington. And last year we embarked on, I moved there actually last year in June of 2012, and we embarked on the Hurricane and Severe Storm Sentinel experiment, which is basically flying these little guys. They're not actually all that little. They're the NASA Global Hawks, and they're drone aircraft equipped, and they're very high altitude. They typically fly 55 to 65,000 feet. And they're equipped with various instruments, dropsondes, various remote sensors, the radar, other things to study hurricanes at large distances. And the goal of the experiment is basically to look at that question of how does the environment, the large-scale environment, impact tropical cyclones, specifically the Saharan air layer. And the reason why this experiment is so unique is that because these are unmanned, high-altitude aircraft, they can fly very long distances for very long periods of time. They can stay up in the air for up to 26 hours, which basically means that even if you're flying all the way over to the coast of Africa, from here, we actually based them here out of NASA Wallops Flight Facility, which is down in Chincoteague, near Chincoteague, Virginia. They can come over to the east coast of Africa and still stay on station for 10 hours, which has not been possible before. So this is a very, very unique experiment. Now, any of you guys who are hurricane buffs know that last year's hurricane season, with the exception of Sandy and the exception of Isaac, actually, so it started off kind of crazy, had a very long lull period, and then had Sandy at the end. But in the middle of that lull period was Hurricane Nadine, and Nadine just started up around September 11th and refused to die. Hung out until October 4th or so. And this is the storm that does not make sense. Basically everything about the storm suggested it should have died. Had high shear, low SSTs, basically everything going against it, and yet it still hung on for weeks and weeks and weeks. So because it was the only storm that was there while we were out there, this is what we flew the entire time. So you can see the different flight tracks that we flew as we had nothing but Nadine to study. And then we finally go out of the field, and then Sandy happens. We're just like, seriously? Just goes like that sometimes in field work. And the interesting thing about Nadine is that, like I said, Nadine did form with interaction of the Saharan air layer going on. And so you can kind of see here the plume of dust that's coming off of Africa here, interacting with the northern and the eastern side of Nadine. And so this is one of the instruments, this is the LiDAR that's aboard the Global Hawk. And these little points here are actually all the dropsondes. This is the other thing that's really cool about this experiment. So we have a rapid-fire dropsonde system that also, because these fly at such high altitudes, the plane flies in the lower stratosphere, therefore we can actually get full profiles of the troposphere with these aircraft, which is fantastic. We haven't had those really in hurricane research before, so this is great. So what you can see here is because it's a LiDAR, the LiDARs attenuate pretty quickly. So it can't see through clouds, but in the clear air regions, you can see this low layer of dust here, and this is again associated with the Saharan air layer. You can see it coming, some of the stuff's creeping in on this side, and also the dust here on the northern side is associated with that. Later on, Sal's still hanging around. There's lots of dry air. You can see the low moisture on this side of the storm, and then also you have the low moisture associated with Sal as well. And you can see that here in the dropsonde. So this dropsonde here is dropped in this dusty, dry air over here on this side of the storm. You can see the constant potential temperature here, the low humidities here in the low and mid levels. That's very, very typical of a Sal profile. Now, the focus of my work is going to be how much of this air actually making it into the storm? And if it's making it in, is it actually making a difference? Because you can see it drops on drop, not that all that far away. I mean, you see some mid-level dry air, which is not unusual for a tropical atmosphere. But overall, this profile has disappeared. So what's going on? Is this an air making it in? Is it impacting the storm intensity or not? This is the focus of the research that we're doing. And one of the keys, I think, to that is going to be looking at the impact of shear. This is the mean vertical profiles, and this is averaged around in an annulus around the storm to get an idea of what the environmental winds are. And this basically is showing that in your upper levels you have this periodic passage of very high wind speeds associated with different troughs that are passing the storm by. Now that's the other thing about Nadine. All these troughs kept getting close to her, but never picking her up. And she just kept going and going. And so what is the shear doing? And does how the shear is distributed through the atmosphere, does that make a difference? Because the other thing that's unique about this is that the shear was really asymmetric. This is the flight track superimposed upon, this is the 200 to, this is the upper level shear, so the 200, 500 millibar shear. And you can see that the zone of high shear is all displaced on one side. So does that make a difference? Does that change how the forced inflow into the storm is impacted from the shear versus if it was completely over the storm center? So, and as I mentioned before, despite all this, this is like 30 meter per second shear. Nadine shouldn't have been alive, and yet she still maintained a warm core through all of that. So again, what made this special? What made her special? What made her different? Because 30 meters per second shear, she should have been dead, but she wasn't. So it's a very, very interesting case. And so with that, I'll conclude. There's lots of, I think lots of really great and interesting work is going to be coming out of this experiment. We're going to be continuing on this year and the following year. So yeah, keep you posted about that. Thank you.
Do you have any questions? So Brian?
I'm just curious about the latest thinking about these primary, secondary rain band formation. In terms of the theory that's going on. And I'm especially intrigued about that down shear right with shear and how those bands can still form under those conditions.
The latest theory is still very confused. How about that? Well, the thing is that people still really aren't sure why rain bands form at all. The innermost, the super fine scale, really close to the storm center rain bands, those were pretty confident are associated with propagating vortex Rossby waves. So just basically propagating waves off of the gradient of vorticity that happens from the eyewall circulation outward. That part we're pretty comfortable with, and there's various different dynamics with those. But those are only talking about the finest, innermost rain bands. That huge rain band complex that's outside of that, no one knows why they're there. Still. So in terms of shear, that's the thing. Because we don't know why they're there, it's kind of hard to know then how the various different factors get superimposed on that to change them. And one thing that is that does seem pretty consistent though is that organization, when you have really low shear, your rain bands tend to have more than one of those principal rain bands, those very large rain bands. They can be two, that makes it more symmetric. As your shear goes up, it tends to go into just one principal rain band. It tends to be in a preferred side of the storm relative to the shear. And it was proposed kind of eons ago now that, that the principal rain band basically forms the barrier between the inner vortex of the storm and the large scale environment. Beyond that, because the thing is, and one of the reasons why, rain bands are kind of a baby because everyone ignores them. And there's starting to be more research into them now, really recently, but for the most part, they've been largely ignored in the literature. So.
Yeah. So for the asymmetric distribution of the precipitation, and the shear.
Mhm.
Is there a simple explanation why you have this asymmetric
A simple-
preference, more aggressive down shear?
I don't know if I would go with simple. Basically, it's even the research on that is really new. I actually just reviewed a paper looking at that was looking at that. And the basic idea seems to be that the shear tilts the vortex in such a way that you get preferred uplift. So if there's no shear, the vortex is perfectly stacked, or relatively perfectly stacked, and that's the way it likes to be. Once you get shear, the upper and lower part starts to get pulled away from each other, and that tilt basically ends up resulting in preferred uplift on one side of the storm and preferred descent on the other. That's the large idea. Getting to the details about that, especially once you start talking about the rain bands, it gets way more vague. But it largely thinking it has to do with the vortex tilt is basically the idea as far as I've been able to gather so far.
Yes, Daniel?
In your considerations of this structure, how much are you concerned with microphysical processes? So you mentioned you produce a lot of ice in the inner eye walls. I mean, these are extreme conditions. You make tons of ice. You said it will be spit out somehow. And if you look in the old literature, I mean, there is this kind of feeder mechanism where ice falls down into clouds, and all your rain bands, outer rain bands, they all start with ice. So you have to have ice out there in these rain bands. And I was just wondering, I mean, if you have a weak, you discriminate between weak and strong storms, you will make a different amount of ice in the inner core, they're spit out. When once you have so much, I mean, you will nucleate everything you suck in there. Then you get a more homogeneous fallout of ice, a more homogeneous precipitation on one hand. On the other side, if the storm is weaker or due to shear, you get it more sporadically, because maybe your ice nucleation process will compete with the relative humidity field, and it's the convection is not so strong that you have these factors. And I'm just wondering, and that goes also with your dust example at the end. Dust is the best ice nuclei.
Right.
And so maybe then you have latent heat, immense release of making ice there, and so you keep this inner core, warm core, longer alive due to the dust maybe. But my question is, are you able to have this kind of microphysical thermodynamics aspects? Can evaluate that with your data or think about that?
Well, there has been, in terms of the microphysics, especially in that the inner rain band region, there are a few things that have been pointed out. I mean, and what I was talking about is just, so you obviously have the ice being generated within the rain bands, in all the rain bands. Yeah.
In addition, yeah.
And that's mostly your lower level signature. Your upper level signature is that ice from the eye wall. And so how that ice is interacting with what's going on in the rain bands is, I don't know. There's an I don't know in that. One thing we do know is that one signature of that just rampant glaciation that's going on in the inner rain bands is the fact that there's no lightning activity, or very, very little, in the inner rain band region. In the outer rain bands, you get lightning. Sometimes in the eye wall, you get lightning, even though not so much, but you do get some. But inner rain band region is a complete dead zone, which is, again, kind of, so basically suggesting that whatever convection that may be carrying, supercooled water, grapple, blah, 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 in inner rain band regions, well, supercooled water will just go away because it glaciates almost instantly. So there's that, at least as far as I've been able to tell, has been the grand extent of, well, not the grand extent, but that's been largely the extent of what has been looked at. Of course, getting microphysics in a hurricane is not easy. So yeah, and I think but I think figuring that out is going to be really important because that is one area that's completely bedeviling the modelers.
Yeah, as soon as you can discriminate the phase, liquid phase, solid phase, it's almost ideal.
Yeah.
Or a concentrated system.
Yeah.
So I think another question from Randy.
Yes, I'm curious about the vertical structure of temperature, particularly on the eye wall or eye cells. Is there any data to show the vertical structure change in temperature?
Oh, are you talking about it in my, sorry?
Well, for major hurricane, the vertical structure of temperature from the surface to the top.
Is there temperature information in
Yeah.
this data?
Oh, well, and are you talking about the HO3 data or just overall? I mean, within the, so within the larger sample, like talking about the TRIM study, that's very hard to do. I mean, because a lot of the instruments that can get that information via satellite can't penetrate cloud. So, I mean, you can sometimes get a snapshot of the warm core of the center, where you have elevated temperatures. But getting that outside of basically getting that anywhere there's cloud, that's not possible with satellite. We do have that with various aircraft studies and things like that, but with Nadine, we do have, or not with Nadine, actually so one of the reasons why I didn't talk about radar data with Nadine is because we do have a plane that's going to be carrying a radar and various other instruments to measure wind speeds. That plane didn't make it to the field in 2012. It should hopefully make it in this coming year. So again, same problem with this aircraft in that we have stuff that can measure temperature profiles and various things in cloud-free regions. But on this, on the environmental global hawks, what we call it, 86, it doesn't have stuff that can penetrate cloud. So it's basically similar problems to the satellite problem.
So I think one of your goals, as you said initially, was to sort of maybe this type of study would help us advance prediction of hurricane intensity. So what's your thought about that? How to proceed in that direction?
Well, I think the most basic way is that having models can. Well, I know there's issues with simulated reflectivity and et cetera, but when you're simulating a storm or simulating numerous storms, this study will provide a baseline of comparison for the various structures that you're seeing within your model. So it's basically saying, okay, is what I'm seeing, is what my model's reproducing realistic? Is it overdoing? Does it seem to be overdoing certain things, et cetera? But in the future, though, I think this, just like I guess with any good observational study, it ended up giving more questions and answers. And I think some of the things that it's pulled out, especially the impacts of SST, I think that's, I want to say that I think when it comes to tropical cyclones, there's a lot of assumptions, and there's a lot of rules of thumb and a lot of ways of thinking that haven't been really thoroughly tested yet, and I think this study started pointing those out. So I think it's going to also produce some directions with what you do with some modeling studies to actually delve into why these profiles are coming out the way. So I think you can do both of those things.
Okay, so let us thank Dr. Thanks, Dr.